All right, Patrick, give us a thumbs up. How's that audio? Okay. Not for ready to start. How did you talk? So just
Test 1, 2, 3.
One of the unfortunate things about Hangouts on air is you can't stop and start recording.
Right.
Once you start the broadcast, I mean, you can have the Hangout ready to go, but once you start the broadcast, you're locked in.
Right. And sometimes you cannot even delete the broadcast video.
Yes, you can go away.
Really?
Yeah, it's pretty straightforward.
Okay.
I've had to do that.
I see. Okay. Because I tried that before, but not so easy.
This is pretty easy. Yeah.
Mm.
This is pretty amazing. Much like the other way I got my friends outside of the department to show up to my flight. I was like, you guys, pizzas from Dazio's. And they're like, I'm there. I'll laugh immediately with, why doesn't iLab get free Dazio's?
Spencer. Good.
They're alive.
All right. I'll be right back.
Oh, sure. Thought we got ready.
What's going on? So you're oh, never mind. My bad. I'm mixing up my courses.
Oh yeah. You're taking data mining?
I'm in Professor McCann's course, and I'm in data science with Professor Fox and cognitive. Yeah, basically. Got the trifecta.
Yeah.
Yeah. So.
Are you taking data science or database mining?
Taking the core class.
Oh, okay.
The problem OS and Ruby's.
Oh, patch, yeah.
All at the same time. Good luck.
Good luck.
Yeah, wow. Good luck, don't die.
Kind of like a test to see how much
Yeah.
Find out.
Shall we?
Yes. I'm ready.
Sure we're. Right. Did everybody find a seat?
Yeah.
Everybody kind of smooshing
pretty
closer
packed.
together. I know it's kind of a packed crowd tonight.
Yeah, it is. It is.
Yes. Hold it down. Okay.
Taking autographs
Yeah,
afterwards, everybody?
hold all your questions until, you gotta keep, okay.
Yeah.
So thank you, those of you in person or online for showing up for our first TWed of the fall 2016 season. Just a little logistics. We are being streamed and recorded live, so just keep that in mind as you ask questions or make comments. We are looking for more signups. Thank you to those who've already signed up. For this term, we're looking for more signups throughout the term. Go to the TWed go to the TWed website at twed.tw.rpi/web/TWed to review the schedule and sign up. We will continue to send out reminders throughout the term to fill up. We're also looking for logistical helpers. Ray is kind of automatically signed up as our audio video helper, but we appreciate any volunteering, and just email me about that. So our first TWed is Rui Yan, he's going to give us an update on his streaming reasoning work. This is, as I understand it, kind of a preview talk for your ISWIC.
Yes.
International Semantic Web Conference. Ray actually made it in. Paper or poster?
Workshop.
Workshop.
Workshop paper.
Sorry. So, but that's very exciting. As you know, ISWIC is one of the top tier conferences that we try to get work from this lab into, and it's really exciting that this work is in, and it's certainly worthy of that. So, without further ado, take it away, Ray.
Thank you, Joe, for the introduction. So, normally the TWed Talk usually lasts for an hour. So in this week, I now talk for an hour. So this is basically an extended version of my talk. So I'll basically cover several details of the backgrounds and my work, so that you guys can get the ins and outs of my work, what's going on there. Okay, so the title is Remembering the Important Things, Semantic Importance in Stream Reasoning. Okay, so the content, I'm going to go through the stream reasoning, which is the kind of the big vision of the stream research area, which is proposed in 2009 by Emmanuel Delabelle. And then I'm going to dive into the problem statement. What kind of problem we're talking about, what I'm trying to tackle here. And then we dive into the semantic importance, which is the conceptual model, which is the notion that I come up with to solve the problem that just stated. And I will be presenting the conceptual model of semantic importance alongside with 2 use cases that implement every aspect of the semantic importance model. And then comes the discussion portion that we can discuss things like how do we generalize semantic importance, and how can we further extend it or add more details, add more aspects, what other potential use case that we can use semantic importance into. All right, so stream reasoning. According to the definition of a stream reasoning from reference 1, it is basically stream processing plus semantic reasoning. Stream processing is pretty powerful and well developed over decades, and now this system is able to process the data in large volume and heterogeneous data, and it can perform pretty quickly. But on the other hand, the stream processing systems usually use their operators that can superficially manipulate the data instead of take a deep look at the data, which is the job of semantic reasoning. So the goal of stream reasoning is basically extract the implicit information out of the dynamic and heterogeneous streaming data of all the physical formats. But usually the stream reasoning object is called RDF streams. Albeit there are tons of different formats of streaming data, the stream reasoning wants the semantics out of the data before it can start processing. And inspired by the RDF and inspired by the success of RDF that they applied in the domain of data management and semantic data management and applications like linked data and stuff like that, stream reasoning area community would like to extend the existing RDF framework and see if it can be applied to streams data. And that actually this is usually the common form of the RDF streams, and we call it RDF streams because they are streaming data in RDF. It is composed usually by an RDF molecule and then a timestamp. RDF molecule is a concept proposed by Dean Lee and Professor Deborah McGinnis in their paper. It is a smallest a group of triples that cannot be further decomposed. A single example, a very naive example, is just one triple, right? Subject, predicate, object. But in the circumstances where blank nodes will be leveraged will be leveraged, then it cannot be further decomposed because blank node cannot be decomposed by by others. So it is called the RDF molecule, which molecules cannot be further decomposed in terms of chemistry area. So stream reasoning can be applied in different areas and aspects. The questions like predict traffic congestion out of car speed and number of cars on highway, discovers the shifts of interest by users by examining the click streams and most attracting content on the web, trends in medical records, and top 10 emerging topics, and the discussion. So basically, stream reasoning covers a bunch of different areas and can be applied widely. So this is why people would like to use stream reasoning in their systems. Considering stream reasoning was only proposed in 2009, it's less than 10 years, there's lots of opportunities and chances to explore, and largely of the field has been remained unexplored. So this is really an exciting area to work with. Okay, so here we go. So with stream reasoning and with the RDF streams, how do people usually process RDF streams to get most of the data, right? So consider this is a one RDF stream, right? And RDF streams, basically one of the assumptions of RDF streams is because they are bandwidths. That means there's like no boundary of the RDF stream. So that actually means there's no way to store a single stream because they are infinite. There's no infinite storage resources to store them. So what people usually do is they actually use a window, which is borrowed from the stream processing systems, where window is a limited sized place where the RDF streams into the window, and the window separates only a portion of RDF streams and process the data within the window. So for stream reasoning, we require the window to process continuous query. That means the window, after each process cycle, the result will be updated by the new incoming data, and the result will be constantly updated as time goes by. But on the other hand, in terms of the reasoning, we need ontologies, we need semantics, and this is usually, and we usually provide the background knowledge in the window so that the background knowledge is encoded in ontology. And by combining ontology, the RDF data, and some reasoner, we can get the result, reasoning result, and constantly window output result. The window is usually has two parameters. One is the window size, basically how many data can window hold, and a window step means like how fast the window advances when the new data comes in. Okay, so here comes the problem. So the traditional window behaves. Basically, the window slides along the data. You have the RDF streams from this, and the window kind of moves along the RDF stream. So each time the window moves one step, and assuming the window step is like one RDF is bigger than it moves one step, and after process that, it moves one step. So you can see that from this, when this window the window moves to solid window, it will get rid of the last one and consumes this and keeps it. And this is actually a first in first out fashion. The data is managed in the window in a first in first out fashion. But this traditional way is not adequate in terms of data management in the following situations. So let's assume that the query is which two numbers is 15, right? So you have window size like this, and you have like 7, 8. Clearly, they can be answers, right? But because window size is just smaller than the distance between the 7 and 8, both of them cannot get into the window simultaneously. That means the query result will never be given. But actually, in this single stream, there is the result. 7 and 8 ought to be the result. But because of the window size, it is not going to be working. And because of this first in first out fashion, because window moves along the window along the stream by moving one step away. So one step the window moves there, then 8 exits the window. 8 get out of the window, but 7 gets in the window. There's no way to hold them both together at the same time. So a no-brainer solution is just to increase the size of the window. But what if like this? The 7, 8 are super long, right? So this solution is not general. It's not general. And in real time, people do not know the actual distance between 2 required data. So there's no way that you can increase the window size this infinite long and preserve the system responsive time, or provide enough accuracy and recall. So this solution is not a good solution. And there are other problems regarding to the first in first out fashion. So we have this window. Window size is 5 seconds. That means the window holds the latest 5 seconds of data, and the window moves 1 data per second. Right. So in 0 time, then when time is 0, and this little figures there indicates the different expiration timestamps of each data. So this means that 7 will be expired after 6 seconds. 4 will be expired after 2 seconds. Why different data has different expiration timestamp? That depends on the data generation, the data generator. The sensor has the ability to assign the different expiration timestamps to data. So it is possible that although data arrives in a certain order, but they expire out of order, it is possible. So consider this is a situation where data has different expiration timestamps. When time is 0, then the window status is like this. But after 1 second, which the window will move forward according to window step, 2 will get out of the window, and 1 gets into, and 8, and this one will get into the window, where I forgot to include the expiration time. Basically, you can see that this one decreases as 2. There are two seconds left, and this 4 decreases 2. So basically, up when the window moves.
You have them all there. It's just your spacing is wrong.
Right. Spacing.
So 8 has a expiration of 6 seconds at the top, and then.
Yeah, basically the spacing is wrong. But you can actually get the idea that when the window moves, the expiration timestamp decreases, and eventually 7 is expired, but 7 is in the window, so which will generate the invalid result. 7, because 7 expired, it has to be get out of the window to provide the enough valid result, right? So after seeing enough pictures showing different statements, just a summary slide to show you why FIFO fashion is not adequate for the following situation. So if the data distance in between is longer than the window size, right? In reality, we do not. There's no way to know exact distance between the required data. So that means that we cannot set exactly a window size to hold all the required data, right? And also, we need to keep the window size small on the other hand. This is because it is beneficial to save computing and storage resources. When the window is big, like this, when the window is big, it requires more memory space to hold this data compared to this data. And when the query runs, it has more data space, candidate space, that both potentially slow down the query execution time. So one benefit of keep the window size small is to, one, reduce the memory consumption, second, to boost the system performance by executing faster queries against a smaller data set. Right. And in the situations where the streaming data itself carries out of all the expiration timestamps that we showed just now here, FIFO just not adequate. And what if the expiration timestamp is determined by other data, right? So one potential example is the positional data where people has a sensor in their feet, and each time when the people moves, the sensor streams a new positional data. So the previous positional data will be expired by the newly incoming positional data, because at one time people only have one positional data. It is not possible to have positional data at one time, right? So, with all these problems and summaries, the stream reasoning systems need more flexible and generalized data management strategies that can help improve the system accuracy and system response time. So, this is also the kind of the motivation of my work, semantic importance. So we kind of know that usually not all of the data in the window is important. Well, because refers to the data there, refers to the previous image. Our query is which two numbers is 15. So we think that those bunch of ones are not that important, because it does not contribute to any kind of solution unless it is a 14. Then 1 is 1, but it's only 7, 8 in there. So we feel like 7, 8 are more important than 1, right? But what's the actual definition of importance? So the data is important in terms of what? This is the kind of a big question. You have to disambiguate this term, right? We need the definition of important. And after spending time in literature review, we actually did not see any related importance definition work we did make, which is fortunate for me because I can fill in, right? So, but on the other hand, we should, before we dive into the work, before we make the work more kind of concrete, we should think of why we should make this, why we should come up with the definition of importance, right? So the beneficial of what if we have, so the beneficial of having an importance is like we can help stream reasoning systems to identify more useful data and then make most of it. We can allow the system to know that when the system sees data, they should immediately know that 7 and 8 are more important than 1, and we can make the most of them instead of spending more time on those ones, right? We can enable other awareness data management, because when we have the importance, we can rank the data according to their importance. And when the data is ranked, we can have some efficient data management strategies that can enable the other awareness of data management. And we can improve system accuracy and recall. We can reduce the system response time, and we can save the computing and storage resources. There are so many benefits if we have the importance defined. So why don't we just dive into that and define importance? And that importance is finally the semantic importance. And its definition is specifically for each datum. This datum, the granularity of the data is in terms of the RDF graph, where one or multiple triples can be included. Its semantic importance is a priority vector, which I'll explain later, with elements preferentially ordered and with no restriction on the number of vector elements. This allows us to consider multiple semantic importance metrics simultaneously while preserving the ability to prioritize some other metrics. Okay, so again, definition. And what is this priority vector? Priority vector is a vector that has, endless. If you can put infinite elements into that, where it emphasizes the first one over the second one. So basically, you have two priority vectors, and you want to compare them, like v1 equals to x1, y1, v2 equals to x2, y2, and then we firstly compare x1 and x2, and if x1 is bigger than x2, no matter how y1 and compares to y2, we say that v1 is bigger than v2. And if x1 equals to x2, then we continue to compare the second element, y1 and y2. And if we have like z1 and z2, then we can continue to compare if y1 equals to y2. So this is the comparison rule of semantic importance and priority vector, and we can use this rule to rank the data. We can use this rule to enable auto awareness. But how do we rank the data? We associate each piece of data with semantic importance priority vector, and we can use these vectors we can use the rule to rank. And this is the conceptual model of semantic importance. Well, it is colorful in the middle, semantic importance, red, and they can be embodied in the priority vector. And currently we have 4 aspects that we have been tested and defined. Query contribution dives into the status of query participation of each data. We have the query and we have the data, and the query requires a system to output the result. But which part of data can contribute to result? Which part of data does not contribute to result? That is a question. And we would like to see which part of data can contribute to the result, and we can make them as important, right? So currently we have frequency and recency as 2 sub-aspects of query contribution. The query contribution frequency, and also we further kind of distinguish the way that data participates in the query by either explicitly graph pattern match or participates in a reasoning process, which requires reasoning, right? So we have query, we have reasoning participation frequency and the query participation frequency, and this is just an explicit graph pattern match, and this requires some reasoning. And also for frequency, we have query participation frequency and the reasoning participation reasons. The frequency is actually a counter of each data that participates in the query. So if data participates like 3 times in the query, then versus another data participates like 1 time in the query, then 3 times will be ranked higher than 1 time data, and that is more important. And the recency is usually the most recent timestamp of the data that participate in the query or the reasoning, so that we can rank them according to the recency timestamp, right? And move here, we have provenance as another aspect of semantic importance. So the provenance also includes the digital provenance, where one typical example is the Twitter, like the content of the Twitter, the timestamp of Twitter, the geolocation, the ID, whatever. And logical and the physical provenance are borrowed from a related literature where they are specifically designed for the semantic sensor networks, where logical provenance usually encodes the matter type of the sensor, like the temperature, it is a Fahrenheit or Celsius. And physical provenance of the semantic sensor usually relates to the geolocation place, the geolocation of the sensor. And also it has a temporal provenance, which is really common, right? We have the generation timestamp indicates when the data is generated. We have a arrival timestamp indicates when data arrives at the system. We have the expiration timestamp indicates when the data will be expired. We have the recent timestamp that usually associated with this recent timestamp, the query contribution recency. And we also have domain awareness kind of as another aspect, and these are enabled by domain awareness ontology. So why we include that domain awareness? It is because usually the contribution and the provenance are usually domain independent, right? So you don't have to know not anything about the domain, but you can just get into the data itself. You can see which data contributes to the query, how it is in the query, where the data comes from. There's not that domain aware. There's not that much domain dependent, right? It's very general. But within the domain awareness, we can make the system more accurate. We can allow the system to understand what's going on in the domain, right? So that's why we provide the domain awareness ontology together with the background ontology, so that we can enable this. And on the other hand, we have trustworthiness, which usually enabled by a trust model. And there are a bunch of trust models in terms of stream reasoning, in terms of modeling users, modeling data, and provide a trusted score. And we can use that trusted score to rank the data as well, right? So with these 4 aspects, we actually implemented 2 use cases, Right. The first use
So
case.
could you actually go back just for 1 second? Just an observation. What you've essentially done, particularly with this query contribution sort of quadrant, is you've sort of created a little ontology that reflects at least the aspects of caching algorithms. These are, most of these are analogous to factors that one can consider in various kinds of cache algorithms. This is the graph. This is the structure which holds it. You haven't spoken to how you weight these or how you actually include these, but you will. But that's what's really interesting about that.
Right. Yeah. Okay. So I have been developing this conceptual model since last year, I guess, and there are different versions, kind of different CMAT versions of this concept model, and I feel like this is particularly, I like this one. But surely there will be more details be added into this conceptual model in the future. Right. Okay. So come back to the first use case, the real-time soccer offset detection. So this picture shows what an offset offense is. This player is at an offset position where this line determines the second last defender, and this player is between the goalkeeper and second last defender, and that this area is called offset position. And when this player is at offset position, and when it interferes with this ball, then it is an offset offense. So according to FIFA law of the game, a player commits offset offense when first the player is at offset position, and we refer this kind of information as A, and then if this player interferes with the play, B. So if A and B, then the player commits offset offense. So for this use case, we have data that players' ball and referees' position data will be streamed by sensors in this kind of frequency, which is really high frequency and a lot of data, right? And our goal is to leverage this positional data, and can we detect the offset offense, right? So, and then we abstract this problem into a stream reasoning problem, because usually A always comes before B, right? And it is highly possible that A and B don't fall into the same window simultaneously, which falls into the first problem statement. Right. So we have decided to use these three semantic importance, the query participation. We say that offset offense basically being at offset position plus interferes with the play, right? And then in order to kind of preserve each of the data, A and B, we ask separate questions like who is at offset position. We can get A, right? And then we ask who interferes with the play, then we can get B. And once we get A and B, we can answer this offset offense, right? We also leverage the provenance, like temporal provenance, like arrival timestamp, which is assigned by the system, and expression timestamp determined by incoming data. And we also provide domain awareness ontology, and domain awareness filtering, which I'll explain later. And this actually shows how the semantic importance of query. So we have failures, right? Query participation frequency and arrival timestamp works. Right? We have the data, like we need A and B, right? And we have other bunch of data, right? And then this window there, it has like this data has like 5 datum, and step is 1 datum. It will move 1 datum each time. And because in this window we ask 2 questions, right? Who is an offset position and who interferes with play? A contains who is at offset position. So we mark A as 1 because this particular datum participates in that query, right? So this is frequency 1. And 2, 4, E, F does not participate in any of the query, so it's 0. And when we rank data according to the query participation frequency, apparently we can rank A first. And then because 2, 4, E, F has all zeros in query participation frequency, then it will be ranked by arrival timestamp, which is like this, FE42. Because I've arrives is the most recent one, and this is the oldest. So we need to rank. And as the window moves, then we can get rid of this 2 because it ranks the lowest, so it's not important enough, so we can get rid of it in the window. And then as window moves, we can see that A places in the query again, so it increases, and the other does not. So we just keep moving until A is the oldest element. So A places 5 here, and the rank is A and I-O. So if this is a FIFO, then A should get rid of it when the window moves, right? But this is not FIFO, this is as I, semantic importance. We preserve A because A is important, right? And we want A stay there and until B meets A so that we can get the result. So when window moves, they actually evict O because O actually ranks lowest. It removes O from here. So O is here, and then B comes in. And we have A and B, we can finally get. This is how semantic works, how things can be ranked.
So it's sort of, I'm not ready to get rid of A yet.
No.
I'm not ready to get rid of it.
No.
A little bit longer. Okay, now.
No. Yeah.
So, just a question. So we're seeing the signal that indicates the offside, but is there a signal that indicates no longer offside, or do you only see the offside? So the situation could be that they, I guess there's the follow-ups. So you have the signal that indicates offside, and then the next is there an interference with the play?
Right.
And I guess if there wouldn't be that second signal if the player subsequently moved in a not offside position. So
Right.
you wouldn't need the signal.
Right. Yes.
If you only need the signal the warning and the follow.
Yeah. So actually, we in the soccer domain, there's no warning kind of thing. So if the player is at offside position, then usually nothing will be actually considered because he doesn't touch the ball, so it's not offside offense. So there's no whistle at all. Once the player is at offside position, and then if it interferes with the play, then that's the true problem. And there's
so
like
the potential offside is just something that you've constructed.
You have, yeah, right. That's actually true. But when the player is at offside position, then in terms of offside detection, this player is more important to others. That's the potential. And if the system is intelligent enough, the system should preserve that, should take special care of that player. And this is also semantic importance that can be leveraged.
Right.
Yeah.
As the ref would do.
Yeah.
They go, I don't want this guy. Okay.
Yeah, just to keep track of that guy. This guy's dangerous, so until that guy commits a fault.
This might be kind of a goofy question, but I was wondering how you actually settle on the size of your window. Because if it's too big, then what's the point if it's too small?
It is. So the window size is how do we set the window size? In terms of this special use case, we actually have annotated our data. That's actually a good question. So we have annotated our data into RDF, into the ontology that we created, and we have run a program to examine how many different triples are there. And it turns out there are only 55 different triples. 55 different triples. So we actually have set our maximum window size is 55 triples, which is why I say this is the window size is 5 datum instead of say 5 seconds, because this is a counter-based window. And the example that I gave way back then, 5 seconds is a time-based window. So time-based window actually can preserve as many data as long as within 5 seconds. But counter-based only can preserve like 5 triples if we set that is 5. And this is our counter-based. We set is like 55 triples as a full size because that many can basically hold different triples. Why there are only 55 triples? It is because the positional data of each player will be replaced by the new incoming data because each player can only have one position data at one time and will constantly be updated. Even though you can see on the string there are a bunch of data there, but it will be replaced eventually. So there are only 35 triples.
Thank you.
Yeah, that's a good question. And I'm going to explain the domain awareness. Right? So we, on the other, so when we actually run this query, the previous query, right? We have only 5 data. But what if we have like 1,000 or 10,000 tuples in the data, right? When we run the query, we see that the data in the window is too much. And it really slows down the performance of the query, right? We want to reduce the data candidate set in the window so as to make the query faster, right? The less data you have, the faster the query is, because the SPARQL query trying to match everything in the window. So the less data there is, the faster the query will be. So we decided to filter out the irrelevant data from the window, right? So for this example, in the data we have A, F, E, 4, 2, and we know that A is relevant and the others are not relevant. And what if we can get rid of the irrelevant data and only preserve the relevant data, right? But how does the system know that it is relevant and it is irrelevant? We provide intelligence, right? An example is that when the player that is at offset position is usually an attacker, right? So the positions of the referee is not important, not relevant. The positions of the attacker's team, the positions of the defenders of the attacker's team is not that important, right? The strikers of the defender's team is not that important, right? In fact, we only consider the second last defender, the ball position, and the attackers of the attacking team. The others position are not that relevant. But
so it's almost like you're masking them.
Right. Yeah. You can you hide them. Right. But they keep coming into the window. So we need to set a filter to filter out the irrelevant data, so that we can preserve the relevant data in the window, and we can run the query against them. Right. So this is how basically we rank. A is important, and F, E, 4, 2 are not that important, but they are equal. So we basically, get rid of all of them, and then we preserve it. And the window moves, right? Window moves A, O, I, M, N, just moves that way. And we feel like A is important at all, and O, I, M, N is not important, then we get rid of it. And then finally we count, and we can get result, and we can rank them, and we can get rid of Q, PQE. We can get exactly the required data that we want for the query, and that's the minimum data set that can be used to answer the query.
But what would be helpful in this slide, Ray, is if you highlighted exactly for example, what the classes are of those, to emphasize this domain awareness.
Right.
Because
Yeah.
you did say it's based on it's ontology based. So these must be from certain classes.
Yeah.
So you
Exactly.
might want to
Right.
highlight that, and so you can color certain things, certain colors, and certain other things, certain other colors. That you sort of do it, but emphasize the classes these are coming from.
Yeah. That's a good suggestion. Yes. Okay, so finally we have some result there, right? So on the left side, you can see that this is the accuracy result. We have one very convenient thing is that by leveraging semantic importance, right? We can not only to implement the traditional kind of management strategies like FIFO, LRU, LFU, we can also implement new kind of data management systems like FIFO DL, which means FIFO with domain layer filter. So this is why semantic importance can be generalized. Because it is not restrict people to use some certain things. It can realize the traditional things and can provide you more kind of real strategies, right? And this CS is the cache size, right? We have 100% cache that's the full cache size, which is 55 triple. And then 75% of cache size, which is 75% times 50. And we can down to 25%. And actually, you can see that as the cache size decreases, the accuracy goes up. You can see the full cache size LFU is 0.0, but 25% of CS is 0.95.
95%. It goes up. Although the average shows that is 94%, but and on the other hand, usually the FIFO does not do the good work when the cache size is small. When cache size is 100%, then everything is basically the same. But when the cache size starts to decrease, you can see that LFU, LRU becomes better, and FIFO just perhaps. This is usually because the first problem statement that distance between data is larger than window size, then it will not get resolved. LFU, LRU will preserve the important data and just wait until its complemented part arrives.
You should
That table bigger.
no. Well, I think that's fine, but you number one, I think you should make sure you clearly label what those values are.
Oh, right.
Okay. Just so you know it, and you might have stripped that off because I'm not sure in the paper we had that nicely labeled. The other thing is, because this is like a screenshot or whatever up there of your stuff, you should, so as not to confuse anybody, I would put like a little reference to the paper on the bottom, just so it's clear that this is yours.
Yeah, it is mine, but it was rejected actually.
Well, okay, but just to make sure.
Yeah.
You could say blah 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 blah. Okay. But just to make sure, because it does look like it's from a paper.
Latex, yeah.
Just make sure that it doesn't look like it's snarfed from somebody else's paper.
Right. Yeah. Yeah. It is mine. It is mine. To the camera. It is mine. Okay, so I have one slide for insider threat detection because this is under implementation. We have all the benchmarks. We just don't have time to analyze the result. But the idea is basically we have a data set. Right? We already have a data set which is much larger than the soccer. We have like 100 gigabyte of insider threat data set. That basically they are synthesized data, including work hours, HTTP action. Yeah. And the data is synthesized, so everything is open. There's ontology out there that people can use, right? So we have the working hours basically indicates when the user logs onto the computer, when it logs off the computer. So the first time they log on, we usually the start time of the work and so on. HTTP action includes the browsing action, right? Which website is visiting, like Dropbox, like WikiLeaks, kind of thing, and internet upload action and download action also falls into the HTTP action. And the file action is basically the open, write, delete action of files. These files are bait, so usually there's a bunch of bait files in the system, so that the different people, if they access to a different computer and try to steal something, the bait file will actually make the people visible because it's a bait file and he knows that.
Bait.
Yeah, bait file, right?
Yes, this is sort of like a honeypot.
Yeah. And device action is basically includes the disk, the removable disk, transfer data, plug into the disk computer and then copy the data into the device file. And email actions like email address, email content, email attachment, etc.
There's something missing, very important that's missing.
What?
Which essentially are the expressions of the policy, the rules that define what combination of this is a potential threat.
That's true. Yeah. That's what's defined in ontology.
In its ontology?
In ontology that we have developed.
I would think that would be the query.
It is. Right. So in ontology, it defines the formation of the malicious actions, and then in the query, it asks what actions are malicious. Okay. So, well, I mean that could generate further conversations, right? But actually, I forgot to include the one bullet point that we created ontology. We actually extended our ontology from the existing CMU insider threat, software institute. Well, I forgot the organization's name, but they actually provide the insider threat indicator ontology that includes a bunch of indicators out there, and they use that ontology to imitate the natural language, to try to kind of convert natural language into the semantic reached context. But on the other hand, they do not define, using description logics, define any kind of class of insider threat, like what is data exfiltration event. They basically just include that term in there, and they do not use description logic to determine what that is. So this is our work. We extend their work, and we can use description logic to determine data exfiltration event. And we can use that logic to provide reasoning in there, combined with the data, combined with ontology, with the window, because the data is streams that streams into that, and with the query, which actions are potentially malicious and which people are bad people, kind of query getting that, and we can detect.
Okay, so now I get it. So just sort of to summarize, rather than sort of explicitly defining all of this in queries, you are defining this based on description logics in the ontology. It's embedded in the ontology, and then you're using reasoning.
Yes.
To pull it off.
Right. Yeah. That's because why we include the formation of malicious actions in ontologies instead of in queries or in programs, because ontologies is more general, you can carry it anywhere and use it. And if you don't like it, you just do it as ontology and apply in the system. But if the program, or the query, then if you transplant that program into other organizations, then that could not be a feasible way. But ontology is essentially a cloud. It's very lightweight but very powerful in terms of the threat.
Oh, and also it could be, excuse me, it could be that your the rules encoded in queries might be too explicit, might be too fine-grained, whereas a reasoning-based approach might allow other
exactly
less explicit but still valid.
It is. And the reasoning-based task actually allows the query to be very simple. The query is like, who are the insiders? It's threatening insiders, and that's it. And the definition of everything will be in ontology, and you can carry ontology anywhere.
Right. So we use trustworthiness and provenance because related to insider threat, and trustworthiness and provenance are clearly can be leveraged. So we actually come up with a simple trust model, and it works. But in terms of the complexity, and it is very simple. And we also leverage the provenance. Is it opt hours? Is it an non-internal email address? Is it a suspicious device? Is it a suspicious HTTP action, like upload everything into the WikiLeaks? That's
And we have that implement that semantic importance into the dataset and come up with the get the result. And we have this discussion. This is the last slide. Yeah, last slide. Right, so we're good on time. So I would like to leverage the last 10 minutes to kind of discuss the generalization of this semantic importance. Right, I already come up with several points, like it fits into the stream routing system to solve the problem, right? And it fits into the scenario where limited resources of computation and storage is very limited, and we can use that. And from the soccer use case, I have already shown that it is able to provide high accuracy and recall. So this can be applied into accuracy and recall, higher accuracy and recall required system. And it also kind of fit into the real-time requirement of processing, because both the soccer and the insider threat, they require real-time, the real-time feature. Insider threat, you have to identify them as fast as possible so as to minimize the loss, right? And we can see that those two different use cases actually is really flexible in terms of choosing which semantic importance to use. Well, actually, depend on different use cases, you can choose whatever you would like to use to wrap the data. Right?
this is the power of semantic importance. Does not restrict you to a certain term. And even though the semantic importance, the semantic importance you want to use is not in the consumption model that I have, but I would be more than happy that you can use whatever you want and just tell me, and I can I can add more aspects in semantic importance, right? And these are all the points of the generalizations that of semantic importance, and I think other points are open up to discussion, right? And also this is actually the one of the questions that Deborah asked me, like, how can you generalize your work, right? And I think that actually answers part of the question of this generalization problem, but on the other hand, I think it is worth discussion.
Right. People have comments, questions.
Yeah, I'm wondering, I guess, like, since you tried a bunch of different semantic importance vectors for the soccer use case, have you been able to make any sort of generalizations or sort of like rules of thumb about what to consider for certain applications in semantic importance? Like, are there, I mean, you've identified, I guess, sort of like a swath of possibilities in your ontology, whereas each individual application may use some but not all of them. And do you have any sort of like heuristic for determining, based on an application, like which ones are more likely to be useful, or how to construct a semantic importance vector?
Right. That's actually a good question, and a really hard one. In terms of the generalization, well, I would be more than happy to come up with this kind of set of rules that can provide a table to help people determine which semantic importance is more helpful in terms of your application or use case. But the goal of semantic importance is to provide you the ability to rank the data rather than restricting the usage of certain aspects of semantic importance. Right? I can do that, but several things restricts me. First, I only implement 2 use cases, and each use case use different semantic importances. The sample space is really small, so if I can use some machine learning stuff, I have no data in terms of predicting. But on the other hand, the goal of semantic importance is to allow people to use whatever they want, right? And the generation of the priority vector is pretty simple. You just place the things that you like more in front, and place the things you don't like in the end. Or place the things you don't want to include, just don't include them in the priority vector. That's it, right? So that's why we say that semantic importance is powerful in terms of, and flexible in terms of its application in different use cases. And actually, different semantic importance will be determined by different use case, and that's one of the claims that I made.
So you can even essentially, like, for given some brand new project somewhere else, you could formulate some sort of machine learning testing over several different semantic importance vectors to sort of do your own self-optimization. Right. So it gives you a parameter to optimize.
Right.
Okay,
if more data will be given. So the reason why I say this is I went to Evan's defense, and he, at the end of his defense, he said that we have this kind of table. We provide a kind of the recommendations of different aspects of his work, and he said that we can do that, but because we have really limited data, the result can be overfit. But he has nothing to do with it because there's really small amount of listeners existing, stuff like that. So that's the reason why I said that. We would be more than happy to use machine learning to predict things, but we have limited result.
Well, what you do for practical purposes, there does need to. So you sort of have to prove the ability to generalize it, right? And to generalize it in a consistent way. So essentially, what it is you've got these different aspects of the priority vector, which you have to combined in some way for the particular application. How do you get that? Right? Okay, so there's obviously some sort of sampling or training that has to happen, some tuning that has to happen. And it can't be man. You know, it has to be. Here is my. Here is the string. Here is the particular set of questions I'm going to present. Here is the domain, you know, as defined by the ontology that I'm going to apply. And now I need to come up with some sort of sufficiency for it. And so, and my approach to doing that should be some sort of a series of tests or whatever, training exercises that produce some metrics that you tune to sort of iterative. It's probably an iterative thing, where you tune that importance. And I would use an example. So the numbers that add up to 15, which you use in the first part. So that's kind of useful and kind of confusing at the same time, because there's a sort of circular reasoning.
Right.
Okay. And the circular reasoning aspect is okay if you've got a tuning scenario that's iterative, because that's kind of the definition of it. You know, how do you find the operating point? You iterate to get to the operating point and reduce your delta to some level where it's acceptable, below some margin. That's kind of what you have to do here. Is you have to, what's the right size? It's whatever is the right size. You know, over the training, you find it, and you've got the sample data, and you tune into that thing. But I think to prove the generalizability of application kind of proves the relevance. You need to kind of come up with that magic sauce that gets to that. And I think the first step is you have to provide examples of how you weigh that. Okay, so it's like, how do you actually choose those different, how to combine those different factors to properly set importance. Then you have to show how you're going to do that in a scalable way for an arbitrary new problem. You know, is it machine learning, or is it some other thing? But you have to sort of be able to, like, here are the different pieces. Here's how I'm going to churn over it. Here's how it's tuned, and it's yes, it is. I mean, that's what I would say.
Right.
I'm totally full of it. Usually I am.
That's a good point, actually.
But I don't know, it seems like there might be something that you could go with in sort of like when you were talking about how to like simplify and rethink the problem for the soccer use case, where you're like, okay, we have two events, A and B, and pretty much every time A is going to happen and then B is going to happen. So we're like, okay, I'm C and A and I'm waiting for B to happen just in case. So I wonder if there's some way you could make like different sorts of like sort of typify different problems is in sort of like one of a couple categories. Like I'm waiting for something to be a member of two classes at the same time. Or I'm looking for the count across some aggregation of things to exceed a certain threshold, or like maybe like sort of to typify the problems in that regard, I guess, sort of like a what you're looking for aspect, and then maybe if there are different strategies for each type of problem there, if that might help.
That's actually very inspiring. It is. It will help. Well, in that way, I think I need to, at least the abstract different types of problems. Like when you say that when you see A, then you wait for B to happen. That's one type, and then there might be some other types that's similar or different, but fall into the same category of this problem. So I feel like that could be one way to make the semantic importance generalized. That's actually the point.
You could have, it's kind of a similar example, but you can imagine you've got a sort of a stream of sensor data, and you are looking for certain conditions, and one of your sensors comes through with a particular threshold value, and that sort of, this is getting very close to event-driven stuff. It's, Google on web dynamics or that kind of stuff. But anyways, but what you could then do is sort of, based on that threshold value of one particular sensor coming through, maybe that enables you, that's triggers you to start looking for a certain set of events that are good potential things that might happen. So you lower the priority of certain variables, you heighten others sensors, you heighten the priority of certain others. Well, how about this? How about this? It's kind of analogous to waiting for that other event. How about this? How about this? It could be a multivariant thing. You know, you're so particular. You're looking for like 3 or 4 variables being in a certain range that indicates you're out of nominal, outside the envelope, whatever. So you're sort of, but maybe there's like 100 variables sensors coming through, but you're only caring about a certain subset of them. And this sort of jiggles you to look for a particular set of those, right? And so you're sort of like you've triggered like, now I have to focus on this. Or this one of the things I have to look at. I got to ignore some of these while these other. So that's kind of plugs into your insider threat. Then there's certain early indicators, you know, that get you into that space, and now you're okay. I know to watch for certain of the following. It's kind of a decision tree mapped onto. There's a certain decision trees that you follow for threat analysis. This is sort of like you prioritize it based on a decision tree given a certain thing up front.
Right. Yeah.
So like this is sort of like what you were talking about with like the filtering of data for the soccer use case as well, where like there's certain players who are never going to be in an offsides position, so you don't have to worry about them.
Right.
So you're already sort of focusing in on that regard.
Right. I think so. You are specifically focusing on that, so you've already decided, you know, your use case is offsides. But the situation I was just talking about is kind of one step above. It's like maybe there's like 5 different violations that you could be watching for, and then that A comes through, which is potential offside, and all of a sudden you're like paying attention for the offside. Like the analogy would be the ref. It's like, you know, watch him, gotta watch him. I'm not looking at him. I'm looking over here to see what happens. So,
right.
Any other questions?
So, at one point you mentioned 55 triples, right?
Yeah.
So that was after it was reduced.
After what?
After the total triples were reduced? Or is that how much you started with?
It is. Yeah, it is how much you started with, and then I reduced that.
Small?
Well, it is small, but the reason why it is the 55 is the number of different triples. It's not the total number of triples.
So, for example, A is B, A, apple, C, A, apple, D would be 1 triple.
Will be 3 triples. Will be 1. Will be 3 triples.
Well, you have 1 subject with all these.
With a load of 3 triples. So player A is at position A. Player A is at position B. Player A is at position C. These are 3 triples with different timestamps. But we see this as one kind of triple because it only describes the player A's position data.
All right, so there's 55 different kinds of triples.
Yeah. Yes. So there are like.
Right. What did you call that at the very beginning? It was the molecule plus the timestamp.
Yeah.
You're talking about that molecule.
Yeah.
55 different.
Yeah. 55 different molecules or different graphs, but each graph will be reviewed. We only use the most latest data with the latest timestamp.
All right. You all set? All right. Thank you very much, Greg.
Thank you very much.
Sign up for TWeds.
Yep.
Thank you those online, including Patrick.